Heists and AI takeovers in Kubernetes, a security tale. I tried to put in as many as keywords and buzzwords I could so that I could attract you all here. A bit about myself. I am a maintainer and tech lead for KubeArmor. It's a CNCF sandbox project. We have applied for incubation. I work as a software engineer at Accuknox. I actively mentor and have been associated as a mentee as well with Google Summer of Code and Linux Foundation mentorship. I'm a proud CNCF ambassador. I'm a volunteer at CNCG New Delhi. Shout out to folks who have come from New Delhi and CNCG chapter. So AI workloads. We have been talking about AI from the morning. There have been multiple talks surrounding AI. How many of you have used, like, consumed AI? I'm assuming everyone, right? That's good. How many of you have locally deployed an AI model and tried to train it? That's a good count. How many of you have locally deployed or on production deployed AI workloads on Kubernetes? That's quite a few. That's good. So this is a generic architecture of what AI workloads look like on Kubernetes. You have your models from Hugging Face, you have your local ML models, you have ChatGPT, Stable Diffusion APIs, you host them in a jump host, or you can directly mount them into the NFS server, S3 storage. They go as a PVC or storage containers inside Kubernetes clusters and orchestrated through kubeflow, kserve. And then you have access to them through notebooks like Jupyter Notebooks, Google Colab, as well as inference engines using PyTorch and a lot of other toolings. This is a lot of things. You have a lot of moving parts in this, and you get confused with all of the moving parts as well. But just the moving parts are not the source of confusion. Now you need to think about securing all these moving parts as well. And that's a lot of task. So just to break it down, securing we will talk about securing later. Let's do something fun. Let's rob a bank. We have two robbers trying to rob a bank vault. The bank vault has a lot of money and they are targeting that. That's what we will set the pretext with. They went into the vault, they found the money, they're happy. But in general, you cannot think that, okay, they just easily went in. There would be CCTV cameras, there would be security guards there as well. They noticed that someone went into the vault. They called the police as well, and the police surrounded the robbers. That's a good thing, right? Police has surrounded the robbers. What the robbers can do now? They have no path to escape. But what you didn't know was the robbers were not there to steal the money. They were there to burn them. What can you do now? Even if the police is there, they cannot do anything. The money is already lost. Even if they arrest the robbers now, the robbers did their task. They were there to burn the money, and that's what they were successful at that. And the bank, whatever stakeholders of bank are, they are all unhappy that, okay, we lost the money. But what if, in a future 2050, you have CCTVs cameras who could automatically know what's going wrong? And then those CCTV cameras are shooting lasers to the robbers. They are automatically activating the traps. This is what the last talk as well covered, proactive security. You have inline security, and you have the robbers stop them and then and there themselves. Even if they had the intention to steal the money or just burn the money, it does not matter. They were just prevented from doing anything at that. So you don't need to worry about the intentions of anyone malicious in general. So we prevented a bank heist. Let's carry that to AI workloads now. You don't want your AI workload from turning good chitty to bad chitty just because someone changed the AI chip and now you have your AI workloads turn evil. With carrying on the analogy of bank robbers, you don't want someone sneaking into your vault and changing the switch from the good chip to bad chip. Now your AI is misbehaving and all of your workloads are impacted. So we'll go back to the architecture again, and I try to identify what could be the source of these attack vectors. You have untrusted models executing in these inference engines and notebooks. You are downloading models from Hugging Face. Local ML models could be modified in anywhere. You have all other sources as well. So primary attack vector is that you are running untrusted models. Then there's a possibility of data poisoning, because you are loading these attack vectors inside the NFS server or S3, and then they are moving to PVC or storage containers. That's an attack vector as well. What if someone attacks at this point or this point and modifies the data? So that's a data poisoning attack vector. And the other things are inference engines and notebooks allow remote code execution essentially. So you have an open attack vector of container breakouts and escapes, and they could always move laterally and cause damage to your organization. So how do we secure them? The first point is that you establish validation and provenance for deploying these models in your cluster. This could be Hugging Face has its trust score, which can help you validate things. You have established, so like you can use OCI, like you can push your models as OCI artifacts today. So those OCI artifacts, now you can use like signing and verification using SIG because they support all sorts of OCI artifacts. You can use them to validate before deploying them in your Kubernetes cluster. But that's all before all of this was deployed in the cluster. What if you have the attack vectors at the runtime itself? At runtime, you have notebooks, inference engines, the jump host itself where you're mounting the models from. These are always running. And what if, as I said, the data poisoning attacks can happen any day. You can have any attacker, attackers are always looking for ways to, looking for all the gaps they can. So there's a need to secure all these entities as well. We'll take a single example from that. We'll check out the Google notebooks. How many of you here have used Jupyter Notebooks or Google Colab? Nice. So if you all know, essentially you are able to write random Python commands in that. Or hell, you can use standard Linux commands as well using python.exec maybe. So that's a source of remote code executions. So what if now the Jupyter Notebook that you hosted, one of your user is just going ahead and doing a kill all command. Your application is going to restart and you have downtime, or they can do anything like that. So that's a source of attack vectors. How do we prevent them? Because this is happening at runtime. So just to give a scope of what kind of attack vectors and threat models exist, you have remote code injection. You have unauthorized access to remote trusted entities. You have a lot of data exfiltration. So these kind of attacks can happen in your Jupyter Notebooks. I've taken Jupyter Notebooks because I wanted to scope in what kind of attack vectors can happen. But all of these carry to any kinds of notebooks, be it Google Colab or R or VS Code, all kinds of code spaces that you host. They are essentially allowing you to execute anything. And all of your data is mounted as a PVC as well. So what if now someone is trying to do something malicious to that PVC through your, like the remote code that you allowed to be executed? So that's something we want to try to prevent. And I want to introduce you to KubeArmor for that. KubeArmor is a cloud-native security, runtime security inference system. So what it does at the end is that you can deny anything like process execution, file accesses, and network operation at a system or a container level. For context, we'll apply a policy. We will explore a policy which can help you prevent the type of attacks that I talked about. So this is a sample KubeArmor policy. We applied that. It needs to be applied on app equal to Jupyter Hub. Jupyter Hub, the notebook that we have been talking about. Now, we have limited that. Inside the Jupyter Hub, you have user local bin Python. So Python, at the end, you are executing Python code in there, right? So you are allowing Python to access network. You don't want someone to go into your binary and start doing apt install, apk add. They can do install anything at that. So this way, this is a whitelist policy because you can see action allow. So you're only allowing network to Python binary. So there's still a possibility that you can execute curl and curl, like any HTTP request from Python, but we have started to limit your attack from here itself, because now at this point you can not use the standard package managers. Now we will explore a bit more. we have marked user local bin, and user bin directory as read-only. So what this means is that anything inside those directory won't be able to modify it. So what the attacker does at first is that it downloads the binary, moves into a user local bin or bin directory, changes its date to something like 500 days ago, so that you cannot detect that, okay, something new was installed. You will see that something from 500 days is already existing, so your static security checks don't mark it as a red flag. So that's the kind of thing. This can prevent that because now you are marking this as read-only. You don't really need to install anything new. Containers package everything themselves. So this covers that attack vector as well. And finally, you may say that what if they execute it from temp directory? It's easy to execute any shell, right? You just do // and name of the binary. But at the end, what we are doing is we have a process match directories as well. We are only allowing execution from user local bin, user bin, and bin directory. So this way, we have reduced what can be executed. We have reduced that wherever it can be executed from, nothing is modified in there. And finally, the network access is limited. So now even if you install an arbitrary binary here, it won't be affected. So after applying the policy, as I said, unknown binaries are not allowed, write to binary are not allowed, users can still read or write through like their data folders and all the things, but whatever is sensitive for you is still secure. So that was the attack vector from Jupyter Notebooks. So this is something Jupyter Hub themselves recommend as well. They have a discourse forum where they talk about how to secure their home directories on configurations, but all of this is achievable through this policy itself. Now, they talk about using AppArmor, SLNX, but KubeArmor simplifies it through because you don't want to attach AppArmor policies to your production workloads because today, workloads are very ephemeral in nature. You can have your workloads running on ARM GPUs. Ampere-based machines are very cheaper. So everyone is trying to migrate to Ampere-based architecture as well. Or any, like AWS Graviton, all the entities from cloud provider, ARM in general has been cheaper. Or you're not using Ubuntu-based machine at all. You're using a RHEL machine. Then AppArmor will fail. So you now need SLNX. All that complexity under the hood is managed by KubeArmor. You don't need to worry about that. You're defining it in a declarative way that at the end, I want so-and-so you be used, and that's all. Under the hood, all of the system level thing is managed by KubeArmor itself. So after applying the policy, we already talked about this. So let's next talk about GPUs. GPUs, anybody has been fed up with the cost of GPUs that, like if you launch a AWS or GCP machine with, if you have a standard machine, it's probably $70, $60 a month. Now you have a GPU machine costing $1,000 a month. Suddenly you have a lot of, and just to experiment, that's a lot of money to pay just for experimentation. So you need to be concerned about your usage of GPUs as well. And recently there have been a lot of attacks on GPUs themselves. So there have been cryptojacking attacks using Team TNT, NVIDIA drivers. They are attacking on NVIDIA drivers. They are attacking on Kubeflow instances. They have Kubernetes cluster in place. So all these attacks are going to ask you to, like, they are going to increase the cost of your GPU. On the other side, they can do a lot of things when they have access to GPUs. They can probably use the shared objects to manipulate your GPU, like hamper your GPU executions of other training models as well, not just hogging themselves. So let's see what we can do to secure this. This is under the hood architecture of how GPUs work with Docker. And similar things happen with container cryo or all other container runtimes as well. You have the Docker daemon, which has an NVIDIA container runtime stream, and runs the initiator. So like the Docker entry point you have is all executed here. But now NVIDIA is injecting its own private container library files inside the container as well, which you are able to access through the NVIDIA toolkit that you imported in the CUDA toolkit that you imported in your application. But how is this helping? Because now this is inside a container. As we talked about securing files in Jupyter Notebooks, we can use the same principles here as well. So let's take an example of now this policy. So in general, what I'm doing is I've blocked access to user lib NVIDIA. So no one can access my library files in NVIDIA. So I have set read only to true so that no one can modify it. And in general, action is blocked, so no one can write to it as well. And when you try to access it from Python as well, because there's a read-only flag, the Python files itself cannot modify it, but they can still, because I wanted to, this was a policy created for a Python application. I've allowed Python execution, but it can be any arbitrary application. If you're using Go or whatever is the name of your application, you can specify that. So this way, you're restricting access to the library file itself, which is your entry point for interacting with the GPU using KubeArmor. Outside of that, you can always do a block list of like popular crypto miners like XMRig, Monero. But this is a never-ending list. You can have someone can modify the name of the binary to something else, and this won't work. So it's always to go better to go with the zero trust approach. So some takeaways from the talk. So Kubernetes has been rising for AI development. People are not worrying about the operations of AI ML models. They are using the already established orchestration framework from Kubernetes. But because it's running at a scale now, you need to understand the attack vectors. It's very important to know what you are running. So establishing validation and provenance is also important at the same time. You can secure against RC using runtime security policies, saying what can be executed, what can not. So that way, even if someone does RC, they cannot do anything outside of what you are expecting from. You have data fencing in inference engines. It works on the same principles of what we did with Jupyter Notebook policy. And finally, you need to protect GPU accesses so that you can prevent attacks like crypto mining. So that's all. Thank you. And I'm open to questions. This is KubeArmor.io QR code. You can check out the KubeArmor project here. Please give us a star. You can join our Slack community. We are always active there. We can discuss about AI use cases. And this is my personal website. You can find my socials here. Happy to connect. Any questions?
We can have one question. Anyone would like to ask?
Cool. I'll be around. Do catch up with me. Thank you, everyone.